Hi, in this video we're going to look at transforming functions and graphs. Now this is a GCSE higher topic, but it also appears at A-level, Core 2 if you're doing AQA. It's definitely an A-star topic. It's actually quite a tricky topic, but I'll go through the main things with you in this video. What we're going to start to look at is basically what are transformations. We're going to look at some function notation that's going to be useful to us. We're going to look at transforming graphs in 3 different ways. There'll be an exam type style question for you to have a go at, and as ever, take revision notes throughout the video, as well as maybe a quick one at the end, just as a way to kind of consolidate everything that we've gone through. So there's a lot to cover in this video. So just thinking about general transformations then, transformations that you know from shapes, what we're looking at here is reflections, rotations, enlargements and translations. Now when we're doing this in terms of graphs, the only ones we're going to be interested in are the following. We'll be looking at reflections, enlargements and translations. We're not doing anything to do with rotations. When we're reflecting, we can reflect in a mirror line, and what we're going to be looking at is whether we're going to reflect in the x-axis or the y-axis. These are the only 2 places that we need to worry about. We're going to enlarge by some sort of given scale factor. So we're going to work out what the scale factor of enlargement is, and we're going to translate by a vector. And remembering that our vectors look something like this, where your top number is your movement left and right, and your bottom number is your movement up and down. So by some sort of vector, I'll call it A, B. Okay, so these are the things that we're going to be doing. As well as that, we also need to be fairly comfortable with what's called function notation. Now you'll see this written down. It might just say f of x equals x squared. So something like f of x equals x squared. All this means is that it means just some sort of function of x, so something to do with an x. In this case, what's happening is the x has been squared. A little bit like you do lower down school when you talk about function machines. What's happened to the x? Well, the x in this case has been squared. If you see g of x, it's just another function of x. The g doesn't stand for anything other than it's the next letter along from f. It's just another function. And if I show you this one, if I said f of x is equal to 3x minus 1, what if we did something like 2 f of x? It just means we're doubling f of x. So in this case, it would be 2 lots of 3x minus 1, which you could expand out. If we had f of 3x, it means every time you see an x, well, we've got an x here, we're going to replace it with 3x. So this would become 3 lots of 3x minus 1. Okay, so we just make sure that you're comfortable with the idea of what's going on here. In this case, a number inside a bracket did something different to a number on the outside. We're going to look at this in a lot more detail when we start looking at the graphs, but this is fundamentally what we're doing. When it says a function of x, if there's something happening on the inside, we might change that x to be, in this case, 3x. So every time we see an x, we replace it with a 3x. If it says 2 lots of f of x, it means like this, 2 lots of whatever the function of x is. Okay, so let's move on. The first thing we're going to look at is translations. Now a translation, it stays the same, it doesn't flip over, it doesn't grow, it doesn't stretch, it just moves around. So let's say that f of x is our original function. And that can be whatever it is. Let's say, again, we might decide that it's going to be x squared or something else. If we've got f of x plus 2, all that means is whatever this function is, whatever values of x that we have, and whatever we've done to x, we might square it, cube it, multiply it by 3 and take 2 away. Whatever it is that we're doing, right at the end of that function, we're going to add 2 on. So f of x plus 2 means 2 has been added at the end of all the calculations that you've been doing with your x. Okay? If it looks like this, it means every time you pick a value for x, let's say you pick x is equal to 0. Normally what you'd do is you'd substitute 0 into your function to see what values you got coming out. Now, what this means is if you pick 0, you're not putting 0 into your function, you're adding 2 on first and then doing the calculations. Let's just have a quick look to see what I mean by this. Let's say that my function is, let's go with f of x equals x squared. Now, if I were to pick a value of x, let's say x equals 0. In this first case, then I would do 0 squared, which is nothing, and then I'm adding 2 on. Okay, so I'm adding 2 on because the f of x plus 2, I get an answer of 2. Down here, what this one means is if f of x is still x squared, if x is 0, I'm now going to do f of 0, but I'm adding 2 on. I've now got 2, and then I'm squaring it. So I did some calculations first in this bracket, and then, remember, the f of x was x squared, so whatever I've got in this bracket here, I'm squaring. Well, in the bracket, the first number I picked was 0, I added 2 on, and then I squared it. So I've got an answer coming out of 4. We can see that these are very different answers, and actually when we start to graph these things, we get very different things coming out too. Let's have a look at the graph. I've drawn here f of x, and I've actually drawn x squared. So this graph here is x squared. I've then said, if I take 5 away from x, from f of x, so I've done f of x minus 5, this red line here, what's happened is the number at the end determines how far up or down this graph moves. So f of x was here, crossing at 0, 0. When I took 5 away right at the end, it's ended up moving it down to minus 5. So the number at the end has moved it down. If this had been f of x plus 1, it would have moved it up to here. I'd have had a curve exactly the same going down at 1 here. Okay, so the number at the end determines the up and down movement. Let's have a look at the one on the right hand side. This says f of x minus 5. Now we can see that this graph's been moved 5 units to the right. Now you might have expected that to have moved to the left because it's minus, but actually when it's in a bracket it does the opposite thing to what you'd expect. It's kind of counterintuitive almost. It's doing something the other way to what you would expect to happen. If this had been f of x minus 2, it would be here at 2. So again, I'm just going to draw that in so we can see. It would have been something like this. Okay, so that would have been f of x minus 2. Right, at this point, I think it'd be worthwhile making some notes and maybe drawing some little sketches. Little revision notes at this point. If a number a is added or subtracted to the end of f of x, like this, f of x plus a, then it's an up or down translation by a vector of that amount. So actually what it's been moved by is, in this case, 0, a. It's not moved anything left and right, but it's moved up a unit. Or if a was minus something, it would have been moved down those units. Here, if the number a is added or subtracted inside the brackets, so for example f of x plus a, then it's a left or right translation by a vector of that amount. Now minus a moves it to the right and plus a moves it to the left. So I'll give you another quick example. If we had f of x minus 4, it would move 4 units to the right and no units up and down. And we can actually combine these sorts of functions. We might see that later on in one of the examples that we do, but that's okay. We can move them left and right, up and down in one go. And actually a place that you will have seen that before, and again something to maybe make a quick note of here, is that you might see that in completed the square form. So when you've got a quadratic that's in the form of completing the square, remember it looks like x minus, let's say, 2 squared plus 4. We can see that two different things have happened. It's been moved 4 units up and 2 units to the right. So in terms of the translation that's happened with this one, it will have been translated by the vector 2 units to the right, 4 units up. So completing the square is another way, another time that you might see this, and actually quite often exam questions will ask you to complete the square and then say, and describe the transformation that's happened from x squared to your new completed the square function. Okay, let's move on. Let's have a look at reflections then. So again, if f of x is your original function, a reflection is seen by a minus sign, and you're going to see it in one of two places. It's either going to be before your f of x, or it's going to be in front of your x. If it's before the f of x, it means it's being reflected in the x-axis. Again, an up and down reflection. If it's in front of the x, it means it's being reflected in the y-axis. Again, a left and right reflection. And the more we see these, the more you'll come to realise that things in front of or behind the f of x are up and down type things. And when you've got something in front of the x, or certainly within the bracket, it's a left or right type thing. And I'm just going to leave it quite vague at the moment, and you'll see as we go through. Okay, so here is a function. Again, I've said that f of x was equal to x squared. Here, I've done minus f of x. So it's exactly the same. It's been reflected in the x-axis. So minus f of x has given us a reflection in the x-axis. Okay, now there was not a huge amount of point in me showing you a f of minus x with x squared, because actually it'd look exactly the same. We can see that we've already got a line of symmetry here. If this part of the curve were to be reflected, it looks exactly the same as the part on the other side. So I'm going to show you a different sort of graph to demonstrate this one. And here it is. I've translated it across just a little bit first. Maybe from a previous one you might know what the function is here. So I'm going to say that f of x equals, can you remember what happens if you move it across 1 unit to the right? It becomes x minus 1 squared, like this. So this was my original function. Then I've done f of minus x. Now what that means is that every time I see an x, I make it negative first. So in this case, if x was 0, it actually becomes minus 0, which doesn't make a huge difference. If x was 1, then it becomes minus 1, and so on, and so on, and so on. And what happens is f of minus x gives a reflection in the y-axis. And we can clearly see that on the picture here. Here's f of minus x, here was f of x, here is the reflection. Okay. Final one that you need to be able to get your head around then, and that's enlargements. Although when we're doing graphs we call them stretches. So rather than an enlargement we'll call it a stretch. And there's two different ways that functions can be stretched. They can either be stretched up and down, or parallel to the y-axis, or they can be stretched left and right or parallel to the x-axis. Again, I've written some stuff down here. It says 2f of x means the function has been stretched by a scale factor of 2 parallel to the y-axis. So it's been stretched, it's been pulled up, if you like, pulled up and down by a scale factor of 2. If there's a number inside the bracket, it means that it's been stretched by a scale factor of a half. That's parallel to the x-axis. And again, it's a little bit counterintuitive. It's a little bit opposite of what you would expect. You'd think it'd be a scale factor of 2, but it's actually 1 over whatever the number is here. So if this was a 3x, so f of 3x means that you've got a stretch in the x direction, scale factor a third. Okay, so whatever the number is here or here, then it's 1 over as your scale factor. And again, let's look at some graphs to see what's going on. In this one, I've used a sine graph. Sine graphs are quite nice to be able to show for two different reasons. One is it's good that you know what a sine graph looks like. Okay, so this goes up to 1, down to -1. The scale along the x-axis is actually in radians. Now you come across that when you do A-level, but actually this would be 180 degrees here, which actually is a little bit more than 3 on this scale. Actually that's pi there, and this would be 2 pi here, but I don't want to overly confuse you. That would be 180 degrees, this would be 360. Now this is 2f of x, the red graph. Rather than my sine graph going up to 1 and down to -1, it goes up to 2 and down to -2. But it still travels along the same period. It has one complete wavelength in the same that it had one complete wavelength before. We still intersect at the same points. It's just been pulled up and down. Okay, so this is what's called a stretch in the y direction, and the number is on the outside. This time I've put the number inside the bracket, and let's see if we can see what's happening here. Again, it's a sine graph. It starts at 0, goes up to 1, down to 1, and stops again. Actually it keeps going, but if we imagine that this is our first kind of cycle here, so imagine that it stops here, then f of 2x, let's see what happened. It goes up and down, up and down. So rather than having one cycle in a period, it's actually got 2. And if this was f of, let's say, f of 3x, it would actually have 3 cycles going up and down. So to go up, down, up and down, up and down, in the same way as before. So we'd have 1, 2, something like that, 3. Okay, very rough sketch, but you get the idea. Something like this. Okay, so you get however many cycles in that period. Right, so if you have a number in front of the f of x, then again it's an up or down stretch by that scale factor. If you've got a number in front of the x, so inside the bracket, it's a left or right stretch by a scale factor of 1 over that amount. It's almost like being concertinaed in, it's being pushed in. Okay, so make a note of this. Right, this is the last bit now. I'm going to give you a couple of chances to have a go and put some of these into practice. This first example shows a diagram here. It says y equals f of x. Here's some sort of graph. It's a weird looking graph. I don't think we need to worry about it. And then it's been transformed in 2 ways. It's been transformed here and it's been transformed here. And you're given a selection of different functions that it might be to match up. So at this point, pause the video, have a go, and I'll explain the answers in a second. Okay, so let's have a look at this first one. Let's see what's happened. Well, it looked like it used to cross the x-axis here at 1 and at -1. Now, it's certainly not at 1 anymore. 1 would be about here. Maybe it's a half. So it looks like it's been squished in. It's been pulled in on the x direction, almost like being concertinaed in. Now, instead of it being at 1, it's now at half. So this, it looks like it's going to do this twice in the same kind of wave, in the same period as what we were looking at before. This is definitely going to be an f of 2x function. It could do 2 of those, or you could say it's got a scale factor of a half in the x direction. The second one, it still goes up to the same values as it did before. Went up to 2 and down to 0, still does. It goes from 2, or sorry, it goes 1 along here, and then 1 along back up, and 1 along and 1 up, which is exactly what it did before. So it's not been, it's not had a stretch in any kind of direction, either in the y or the x direction. It looks like it's just been moved across. It looks like it's been moved. Let's see, was at -1, it's now at -3. It's been moved 2 units to the left. So 2 units to the left, that must mean it's within a bracket. So let's see, which one could it be? I think it's going to be f of x plus 2. Positive values move things to the left, negative to the right. So that's the answer to this one. Okay. Finally, here's the last thing for you to have a go at. This is the graph of y equals x squared here. On the same grid, I want you to have a go at sketching out, or using your own paper, have a sketch out of the graph of x plus 2 squared. Sketch out the graph of y equals x squared minus 3. And then finally, describe the transformation that maps y equals x squared onto the combination of both of these things. So y equals x plus 2 squared minus 3. Pause the video, have a go. Okay, so the first one, y equals x plus 2 squared. This plus 2 means that it's shifted the whole graph to the left 2 units. So that would be something like this. Okay. The second one, where we've got this going on, x squared minus 3. So that must mean it's come down to 3. So again, we're going to have a graph that looks something like this. And finally, describe the transformation which maps y equals x squared onto the combination of both of them. Well, that must mean that it's done both things. So to get from one y equals x squared, which is the black graph, to minus 2 along and minus 3 down, my graph's going to be somewhere here. Combination of both. And again, this is incomplete to the square form. We can simply say it has had a translation by the vector, so minus 2, minus 3. It's if we think about the point at the very bottom of the graph, this point down here is now here. It's moved 2 units along, 3 units down. And that's how we can describe it with a vector here. Finally then, last little bit of revision notes for you. If you notice that there is some sort of change on the outside of the f of x, then it's going to be an up or down change, whether that's a number in front which is stretching it, or a number at the end, either plus or minus, that's translating it left and right, or a negative sign in front of the f of x, which is a flip up and down. If the change is on the outside, then it's an up or down change. If the change is on the inside of the bracket, then it's going to be a left or right change. But be careful that sometimes, or more often than not, the ones on the inside are not what you would expect. So if it's plus something, it's moved to the left. If it's a minus something, it moves to the right. If it's a 2x rather than x, it means it's a scale factor of a half. If it's a 3x, it's a scale factor of a third. 4x, scale factor of a quarter, and so on. If you want to practice any of these things, I would recommend using some software that you can use it online, called geogebra.org. download the software. It's really good. You can have a play around, particularly with these sorts of functions. And if you're going on to do A-level, then it'd be definitely worthwhile getting good at this sort of topic. Okay, as ever, good luck with your exams. Hope everything goes well for you. Keep checking out the YouTube channel, subscribe for new videos, and look out for @Tupton Maths on Twitter for releases of new videos. Okay, bye.